All right, thanks everyone for having me. My talk is very much a lower level tactical talk compared to Jack's. I really love Jack's talk. This idea of thinking strategically and working strategically with software is just, it's an old problem, as he mentioned. We're still wrestling with it. We found good techniques for certain aspects of it. I was not aware of contraband. I'm pretty excited to check it out after our meeting today. So thanks for introducing us to that, Jack. So what is inline? This is basically a new feature in Scala 3 that you may have heard the word before. It's been used in other languages for a long time. It's usually a construct that tries to tell the compiler or compel the compiler to like expand a block of code inline in the stream of output bytes or whatever, rather than like do a method call or whatever. And that's exactly what it does here in Scala. And so we'll explore, why it's useful and how it's used a little bit. These notes are actually online. There's this link here at my deanwampler.github.io site /inline.html. You'll basically find these notes if you want to play along at home. I'm actually going to demonstrate things live here. I started SPT on the right-hand side using the repo from my example code in Programming Scala 3rd edition. So there's a couple of links here where you can find out more information. I work for Domino Data Lab, which is builds like an enterprise level suite of tools for data scientists and ML ops and so forth. Be happy to talk with anybody about that offline. We are hiring in some cases, so feel free to reach out if you're interested in like writing Scala code or being involved in some other way. And you can follow me at Dean Wampler on Twitter as well. So the next links, and actually all these links again are on this inline page, just to click through a few of them here, see all they'll kind of trigger your memory when you see them later. Here's basically the same notes on my website. The font is a bit big for some reason. And then it's also linked to this page about the 3rd edition of Programming Scala, which covers Scala 3 and came out last month. So if you're interested in learning about Scala 3, hopefully you'll find this book useful, even if you're an expert in Scala already. I have been blogging about Scala 3 features, and I do have a few blog posts about inline, which is this one down on the left, and then the macro features. There's a few more things I need to post about, but that's another way you can kind of learn a little bit about it. This happens to be the one on inline, and I started with this little screen grab from a tweet that T. Polecat tweeted not long ago about how everybody obsesses about macros. You can also go to the Scala Lang website and find a lot of documentation about all this stuff. And again, the code samples are actually freely available on GitHub if you want to just play with some of the code. It's not well commented because the book provides comments, but nevertheless, you're welcome to grab it there. Okay, so anyway, going back to this. So the idea with inline is that if you, and it's a keyword, it's not like an annotation or something. If you attach it to a method definition, then it will try to replace the body of the method when it generates bytecode with the logic that's inside the method. That eliminates the overhead of invoking the method, but it could also expand the bytecode if it's like a big method. Then you're suddenly introducing a lot of bytecode, especially if it's called a lot. So there's this trade-off in all of these cases where you inline something of, is the overhead that I'm removing actually overwhelmed by other kinds of overhead like bytecode overhead. You can also do conditionals, as we'll see. So what's cool about this, and the inlining can only happen if the compiler can determine at compile time values that you specify. So things have to be constant at compile time, as we'll see. But you can inline conditionals, which means that in runtime, the conditional won't actually be evaluated and then either or branch taken. It will just insert the bytecode for the branch that is going to be taken no matter what. I didn't actually put the bullet here. I forgot to do it, but it also works for for pattern matching, match clauses, and I'll show you an example of that. So anyway, let's actually look at some examples. Here's a method definition. It's just a recursive method that calls repeat, and basically what it does is it concatenates a string with itself n times or count times. The only difference between this and a regular method is this inline keyword. And you'll notice that if I call it with a two static values, hello and 3, are runtime, or rather compile time knowable, then it just works. If I try using like, a value like this, n equals 3, and then, let's do this, then this is going to fail. And you also get this interesting error message. They can only inline up to 32 times. That's kind of an oddball error message. It should just be saying, look, you gave me something that I don't know for sure is actually a constant. So I'm not even going to try to inline it 32 times, which is the limit. Now, it's a bit strange, I think, that it said, wait a minute, shouldn't n be known to be 3 because I declared it a val? Well, you can actually do this if I make inline a val, so we can do declarations like this. That means nline disappears completely from the, or sorry, n disappears completely from the bytecode. Instead, it's now just going to literally insert 3 here, and then it just works as we expect. Okay, so, and I'm just kind of showing you what happens here. And just let's think about performance for a second. Is method call overhead really that bad? Now, it probably would make a big difference maybe if this was going to be, a really big thing. But, we have this limit of 32. So let's just try it. Here's another definition of the same method where it's not inlined. Otherwise, it's identical. And I'm also going to define this little method that will use the Java lang system nanotime to, like, get the time before I run this, whatever it is I'm running, get it afterwards, and then calculate the difference and see what, how long it takes. So if we try that, and I'm actually showing you a session from yesterday when I was playing with this, and the number actually varies a lot. And I think there's a little bit of, the JVM doing its usual thing with, hotspot and so forth. So the numbers can actually vary quite a bit. And I'm not yet getting down to the number that, I have here, 4,500 nanosecond. So there's a lot of other stuff going on. Zoom is consuming CPU. These numbers are really just kind of for entertainment value. You don't bet the company on this because they do vary a lot. But nevertheless, it actually does make a difference. There's a, it's roughly anywhere, when I did this yesterday, I got anywhere between like 30 times better performance versus just down to like 2 or 3, just by not doing method calls, but inlining all of that code. And in this case, if we did something like decompile this code, we would see this big chunk of code where it actually just inlines these expressions 31 times. And if you do 32, then you hit that limit. That worked, holy cow. Let's try this again. Oh, I'm doing the wrong one. This is the one that's not inline, but if I go back to this, then we get the same error we saw before. Okay. Let me check the chat here. Someone's asking a question. Inline like C++, exactly. So it's, I think C++ is a suggestion to the compiler, if I recall correctly, whereas this is actually going to fail the compilation, as we saw when I used a variable n, or a val n, and then it failed. That's another limitation besides the question of code bloat and so forth. So actually what has happened here is that, well, actually, I'm skipping ahead a little bit. Let me come to this second version, which is where I'm also going to inline the conditional. So notice there's an inline in front of the if now. And so this is actually really cool, I think. So what is actually generated in the bytecode is that it will actually evaluate count at compile time. And when it's not 0, then it's going to do the else clause. It will insert s plus for p2, et cetera, et cetera. But if it is 0, it's just going to insert empty parentheses. And in fact, well, as we saw earlier, we can, if we try this, let's do this, p2, and actually I wanted to use the n again, although I've already inlined that, haven't I? So let me do another n. This time it's not inline. I'll do 3. And we'll see again that we get a different error this time, that we can't inline the conditional expression because we're not using something that's a constant value. Notice this expression right here. We're actually going to see how to do that by the end. I'm going to show you a macro that can insert the code that failed in a situation. It looks like they're doing exactly the same thing in the compiler, but it's after it's been desugaring the operator overload notation, or operator inline operator notation. So it's calling the method equals on this integer. Okay, Well, if we actually decompose the bytecode and then sort of reverse engineer it, we really are actually inserting bytecode that looks exactly like this expression when n is 3. The first time, if you go back and read what's happening in the definition here, the first pass through this function count is 3. So this if clause will be false, and it's going to insert s plus the next call to repeat 2. Well, that comes back in and inlines again. Count is now 1 or 2 rather. So it's going to insert the same kind of code. And I put in parentheses just to show how things are scoping a little bit. They're not, what you would really see in the code. Finally, when we get to count equals 0, then it just inserts the, the empty string. And so literally it's as if we typed in this particular code right here rather than a function or a method that did it. So it gives us the potential to do some interesting performance optimizations, especially for something that's used a lot, that's relatively small, where the method overhead is significant compared to the execution time of the method. And it lets us possibly do a lot of interesting optimizations. But the reality is, because there's so much going on in a JVM that's running, you should really profile things and try to ascertain if this is really giving you the benefit you think it is. And also keep in mind the limitation that you can only call this repeat 2 or repeat the original one if you can pass constants at compile time to the as arguments. Okay. And if we run the time on this, let's see, let me just do n, or actually 31. And it's pretty comparable to what we had before. Again, I think there's just so much going on internally that you're not going to see a big difference in performance, but you might in other contexts. Similarly, we could also inline match clauses like this. And it's going to behave exactly the same way. If I just go back up and repeat this one, the time is going to be roughly the same. And once again, the behavior at compile time is exactly the same. When count is 0, the byte stream will just have an empty string. Otherwise, it will have the string plus whatever gets inserted next, as we call this recursively. And so this has to be evaluated at compile time. Okay, so that's sort of the gist of inline. It was introduced as part of the new metaprogramming facilities in Scala 3, the totally new macro package. And when you do compile time macros, you combine inline with the so-called quoting and splicing in macro definitions. It turns out there's even a way to do runtime macros, which I haven't blogged about yet. It's a bit harder to get your head around it, but you'd actually use the same quoting and splicing that I'll demonstrate next, but without inline, so that it's something that can be processed at runtime rather than at compile time. So let's look at a non-trivial example. So speaking of looking at old ideas like model-driven architecture, one of the old ideas that I was really into back in the 90s was called design by contract. This was invented by Bertrand Meyer, who was the creator of the Eiffel language, if any of you know what that is. But it's really a great idea that we've sort of replaced with test-driven development, kind of. And that is the notion that if I have a module of some kind, I should be able to specify preconditions that have to be true when someone uses it. In other words, that's the contract that they have to satisfy. Post conditions that were promises that I make about results that I'll return if the preconditions are satisfied. And then invariants that have to hold throughout the execution of the module. And so what we're going to do is write a macro that implements an invariant for us, so that what we'll do is we can specify a couple things. First of all, we can say that I want this invariant to be true both before and after the code executes, and write it in a very concise way. But also we'll support the ability of compiling away all of this overhead. Say we want to do this during testing, but we decide that during production, we don't want the overhead. It's really just a test mechanism. And I say I'm sort of hedging the way I'm describing this because there's some cases where you may really want to check invariants at runtime, for safety, but we'll just assume that we want the flexibility to completely not only turn it off, but completely eliminate it altogether. And you could think about doing something similar with a logging library, for example, where you only build up that message string, or you only call the logging subsystem if you have some sort of compile time enablement turned on. Otherwise, it's turned off. And I'll come back to a drawback of that in just a second. But so this is taken from the, again, Programming Scala 3rd edition examples. And these comments basically tell you where to find the file in the examples. And this was in a package I called prog scala3.meta. And I'm importing something that part of the macro system called quoted. Also, if you haven't noticed, Scala 3 goes to a more traditional view about wildcards for imports, and it uses star now instead of underscore. That's actually a breaking change. Some changes are made to be, you can use old idioms and new idioms, mix and match, and then eventually the old one will go away. This one, they just said, it's done. No more underscore. So I'm going to put this in some object called invariant. And here's a compile time flag. Notice I'm inlining it. So this variable is going to disappear from the bytecode. And I'm going to set it to false, meaning that I want to, when it's set to false, it means I do want to do the checking. Maybe I should have done the opposite because it's a bit, it's a double negative in a sense. But if you set ignore to true, then it's going to get rid of everything at compile time and just evaluate whatever block it is that you want to do. By the way, this is one slight difference with the way like the assert function works in predef, where some of those functions and its siblings, you have to be careful about putting a block of code inside the assertion that you absolutely always want to be evaluated, because in some cases when you turn off those assertions, the block also disappears. In this case, the block doesn't disappear. It will always be evaluated, even if I've turned off the invariant checking. But I'll have to do that at compile time. So that's one disadvantage. I can't do this at runtime or with like a flag in like a config file or something, because I need this to be determined at compile time. And so that's why I'm using this inline val in this case. Okay, so the what I'll do is I'll call this thing. I didn't put an example in here. I probably should have done that, but I do have one in one of the blog posts that I showed you earlier. Anyway, I'll do something like invariant, and then what I want to be true in parentheses, that's this predicate, and then some message if it fails. That will be added to other information that I'll show you in a second. And then finally, as a separate argument list, the actual block of code that I want to be evaluated. And notice that all of these things are declared inline. I did mention earlier that you can declare arguments inline as well, and that means that any of the bytecode for handling these variables will disappear, and it'll just inline the actual values that I specify in my source code. Oh, and so what's going to happen is the same sort of conditional behavior that we saw a minute ago, where if I'm not ignoring this invariant check, then I'll test the predicate. If it's false, then I'll call this fail method that we'll look at in a second. And I have this argument before that shows that it failed before I evaluated the block versus failing afterwards. I'll call the block, saving the result. Then check the predicate again to make sure it's true, and assuming I get this far, fail basically throws an exception. Then I'll return the result. Otherwise, if I'm ignoring my invariant checking, I'm just going to inline the logic for the block, and that will just be whatever this call is, or this code that I'm writing here. So anyway. To dive into the details, and now we're getting into a little bit more of the macro implementation. This function, this method also has to be inline, because we're just going to insert the block of code. We don't want to really call anything. And what we're doing here is something called a splice. It sort of looks like the way that you would do like interpolated strings. That's a deliberate choice, where I'm going to insert into the byte stream whatever the logic is for fail impl, and this will actually just be a regular method call that implements throwing the exception. And then I pass these quotes. Notice the old like symbol syntax where it's tick and then a variable name, and that turns each of these things into this expression object that comes out of Scala quoted. it represents the thing that I'm evaluating. So I'm going to pass in quotes for all of those four things, and then fail impl. It takes now expressions of these types that I had up here, and then it builds up this big quoted string where it's actually going to do the throw exception. I define some invariant failure type, which I don't think I listed here. Oh, here it is right here. Yeah, okay. So it's just an exception. And then I'm going to format an error string. And the key thing I'm going to do is actually show, the details of the expression and also, whether it failed before or after, as well as the block. So this will actually expand to show me the actual code that failed, not just, you say something blew up on line 5, and then I have to go look at the source code to see what it's talking about. And all this show expression helper does is it does a nice conversion from an expression of some arbitrary type t to an expression of string type, because I just want to see what the code looks like. So I'm actually going back to the source code at this point. So if ignore is true, then we're just going to insert the block again, and we'll not do any of this predicate checking whatsoever. That will disappear from the bytecode. Otherwise, this is what the bytecode will have in it, the equivalent of this. And then fail will throw an exception for us. Okay, so let me quickly, if I should have actually shown an example of this, and I can do that by going to my editor, and I'll bring that up, not this one. I think it's this one. Yeah, so let me bring that up. And I think I have a test in here somewhere. Yeah, let me just go to the test suite. So, and I just basically did a Scala check style test. And so it would look something like this, where I'm going to insert that this variable.s of this object that I won't go into the details. I'm going to insert that variable doesn't change some value that it, notice I captured it going in. I'm going to make sure that value doesn't change. I'm going to manipulate this object inside the block. This is the block that always gets evaluated. In this case, I'm creating a failing test because it will actually modify that variable, and then I'll get this invariant failure. So, but the key point is, and the highlighting is a bit strange, I'll just do that and then undo it so you can read it. But so you do just invariant condition and then whatever block you want to evaluate, and then it magically does this checking for you. But if I recompile this with that flag set to the ignore value set to true, then all of this would disappear. The test would then fail because it wouldn't throw the exception, but that's the way I could turn this off at runtime. And I'll add this example to the my website code because I kind of left it hanging there a little bit in kind of a dumb way without providing an example. Okay, let me check the time. I think I have 15 or 10 minutes left. Is that right? Or,
yeah, you're all good. You've still got a bit of time left, so feel free to carry on.
Let me just talk about a few subtleties quickly with inline, because you're manipulating, it looks like I'm calling a method, for example, but I'm actually not now. So it has some implications, especially when you talk about inheritance, that are useful to think about, although they're not terribly obvious. So here's an example where I'm going to override something. I have some trait T that defines a couple of methods, one of which is abstract, the other is concrete, but it calls the abstract one. And then I'm going to implement it with some object O, and I'm going to declare both of those as inline implementations. And in fact, override M2 to make it inline, which is okay. And then just have it actually change what it does. It returns a different string as a result. And if we run this, we'll see that oops, that's not what I wanted. Let me get rid of this. So that works fine. O.M1. I think I typed 0. Yeah. And then O.M2. So notice that O.M2 does what we would expect. It's adding this extra string. But notice also that kind of in the way we would expect, if I assigned a value of type T to O, and I can call those, and I get the same thing. So this behaves like you would expect. The only interesting bit is that even though I didn't say explicitly that the trait method should be inlined, I can do that in a concrete implementation if I want in a derived case. Even something like this, I just had to override it. It does get a little bit interesting though if I make the trait method definition or declaration, I should say, itself inline. If we do that, then it turns out, let me just do these first so that we'll see that they work. So once again, same structure, but now this is inlined instead of being declared not inline. But now this is not going to work, and we get this kind of interesting error message here. So T2 doesn't know, even though it's pointing to a concrete object that implements this method, it won't let me actually call the method. I just get this error, deferred inline method in trait T2 can't be invoked. Whereas that just worked fine when in the first example like this. So maybe the point is probably don't want to declare inlines on traits. Inline is an optimization in some degree, and it's also, of course, part of the macro system. So probably not a great idea to declare inline on something like this, like I did here, but just leave it open to implementers to decide whether to inline something or not, because you get this slightly unexpected behavior. There's another keyword now in Scala called transparent, and this logic is counterintuitive. It's possibly useful in some cases, but it's also maybe not in others. What this effectively does is that it actually allows the compiler to determine that, oh, there's one case where I'm going to statically know that I'm going to return a T2. Again, I declare this method as inline. And if B is false, then I'm going to return a C2 object, which is a subclass of C1. And it will actually know in the bytecode that the thing that was returned in that case is actually a C2. And even though I declared it to be a C1, I'm allowed to treat it as a C2. In other words, just to be clear, in a normal object-oriented model where I don't have inline and transparent, I could never really make the assumption that I'm getting a C2 back from this make method. And now I could downcast and hope it doesn't fail, but I'd always have to only assume that I get a C1. But in fact, the compiler knows in the case where I pass false that I really do have a C2, and it even lets me assign the result to a C2 without a cast. And it lets me call methods on this thing, and because it knows it's a C2. So I'm not entirely sure why they added this. I suppose it could be useful in some context, but because it breaks our usual intuition about subtyping in an object-oriented context, I think it could be, more confusing, more surprising than beneficial. But anyway, that is one thing you can do: declare something, a method, transparent inline, and then the compiler will actually be more aggressive about the return type that it allows. If you're returning subtypes of whatever it says you're returning. So that's pretty much all I wanted to say about inline. I think I pretty much covered most of the details and then showed a kind of a non-trivial example that's kind of similar to the error message we saw up here, where we actually saw the code that failed in this particular compilation example. And you'll notice that it complained that, once again, it gave us the expression after handling the syntactic sugar of operator method call kind of syntax. All right, hopefully that's reasonably interesting, and I'm happy to take any questions about this.